When you turn this video off, please tell me what the reason was so that I can improve. Otherwise, hi and welcome. I'm trying to learn electrical engineering, today electrolysis, and after we've done it, we're going to do extensor carpi ulnar strength training. Here we are. If you participate in the extensor carpi ulnar strength training, then it's relatively honest. Copper sulfate solution between copper electrodes. So we're having a copper solution and then we're having two copper electrodes. This is part 2 to electrolysis, but we don't really understand it. The ions present are Cu++, H+, OH-, and SO4-. At the anode, so we are at the anode, okay. OH- and SO4- ions have migrated towards the anode, but neither of these types of ion lose their charge. Instead, some atoms in the copper anode lose 2 electrons each to form copper in ions which pass into the solutions. Okay, two things, I don't get it. OH- and SO4 have moved to the one copper plate, to the anode. But they have moved there, they're not giving something there. The copper plate is giving something to the copper solution. That's the trick. We're having copper solution and copper plates. And so it happens that the things going there, but they're getting things from the copper plate. They're not giving something there. At the cathode, the choice here lies between the copper ions and the hydrogen ions. Both with positive charges and called cations, because they both migrate towards the cathode. The copper ions are selectively discharged, causing the cathode to become coated with a layer of additional copper. Okay. We're having copper plates and a copper solution. That means at one place we have anode and cathode. At the one place the current, the electricity comes in, and the other place out. Now, to the anode, I still don't get it which is doing what. The copper from the solution goes to one plate, but it is not giving its electrons away. It is getting some from the plate. And at the other place where the current is coming out in, some things are going there as well, and they are now giving off copper. So the copper solution gets at one place copper, and at the other place it gives copper off to the copper. And now the copper plate gets a copper layer. In the electrolyte, copper ions are removed from the anode to enter the solution, and an equal number of copper ions leave the solution to be deposited on the cathode. The solution of copper sulfate remains unchanged in composition and concentration during electrolysis. In this case, we are having copper as copper liquid and a copper plate and a copper plate. At one place, electricity comes in, where the copper things go to it, maybe it's the other way around. The copper things come to it, and they're getting now copper from the copper. The copper solution gets copper from the copper plate. Our copper goes to the cathode, where the electricity goes out again, and now they are giving copper to the copper. And we're having here a copper plate, which gets rid of copper, and another copper plate, which gets more copper. And in the solution itself stays the same amount of copper. Practical applications of electrolysis. Oxygen, hydrogen, and chlorine gases are all produced commercially by electrolysis, although the two former gases are produced more cheaply and on a larger scale by other methods. Okay, these electrolysis is somehow used, it isn't really explained so far, to make oxygen, hydrogen, or chlorine gases. So that whole thing is to produce things, to make money. Consideration of the electrolysis of copper sulfate solution between copper electrodes will suggest to you that this forms the basis of a process known as electroplating. For example, a brass spoon could be nickel-plated by filling the bathing bath with nickel sulfate solution and providing a bar of pure nickel as the anode. Articles are chromium-plated and silver-plated in a similar sort of way. It should be pointed out that the choice of salt in the particular plating bath, the concentration and temperature of the electrolyte, the actual material to be plated, the cleanliness of the surface, and the size of the current used are all factors which affect the final result. Much trial and error is often required before successful electroplating can be carried out in the laboratory. Now our setup where we're having copper at one side, copper at the other side, and for some reason that copper gets even more copper, is used to make a glasur to things. What was it called? To make whatever. Plate. If you have a spoon, it can be that you want to have a nickel spoon with a nickel on top of it. Or you have platinum and you want platinum around it or something, so you can produce things with it. And you're having at one side the copper block, the nickel block, at the other side our spoon, and in the middle our nickel solution. And now some parts of nickel go into the anode where the current comes in, taking nickel from the nickel block, and other parts of a nickel solution go into the spoon, and the spoon there's the electricity going out, and they're now giving the electrons of the nickel to the nickel spoon, and the nickel spoon gets glazed. One other practical use of electrolysis is the process of anodizing aluminium. Anodizing aluminium. An aluminium article is made the anode in a voltmeter containing an electrolyte and a dye. The color produced is due to the absorption of the dye molecules by the hard layer of aluminium oxide, which forms on the aluminium. I think it's just the other way around. The color produced is due to the absorption of dye molecules by the hard layer of aluminium oxide, which forms on the aluminium. Okay, it's the same, just not that it gets a glasur around the nickel thing, but it gets a color around it. But it's the same process. The color molecules are moving there and they're staying on it. Corrosion. When iron rusts is the name for it. I searched the name. Leaves are not fouling or something. I don't remember what it was. Leaves are not fouling. Iron is rusting. So when iron rusts, or for that matter, when any metal corrodes, a liquid must be present, even if this is only the dampness of a surrounding atmosphere. There has to be a liquid present for rusting. There has to be, it's not just it goes fast or something, there has to be. Even if this is only the dampness of a surrounding atmosphere. In effect, corrosion is the result of chemical changes taking place in small voltaic cells set up on the surface of metal. This is exactly the explanation of local action in a simple voltaic cell too. A zinc rod containing particles of copper or carbon as impurities will readily dissolve in dilute sulfuric acid or any other acid. Each speck of carbon embedded in the zinc, so the carbon is the thing which should not be there, it's not completely clean. Each speck of carbon embedded in the zinc forms a tiny voltaic cell giving off hydrogen, while the zinc forms ions to go into solution, hence the dissolving or corrosion of the metal surface. Okay, we're having, I don't know what a rod is with a cable, we're having a zinc spoon. And our zinc spoon is not completely clear. There is some carbon in it, for some reason, because whatever. And now, where this carbon is, if there is no dampness there or water, it seems to be that you need a liquid. It is now a reaction happening with a dilute sulfuric acid. Where now that comes from, I don't know. Maybe that is somewhere a little bit in the water, whatever. There's no reaction happening, and at that place a volcanic cell comes, and that gives off hydrogen, so the carbon inside of the incleanness, or what it's called, the incleanliness of the zinc, the carbon, is reacting with the dilute sulfuric acid, wherever it comes from, maybe from the rain or whatever. And at that place a voltaic cell appears, and it gives off hydrogen because the carbon is reacting with the dilute sulfuric acid. And the zinc also forms the ions which go into the solution, and therefore it dissolves or it corrodes the metal's surface. Now consider the iron pipe lying in wet ground, which it is intended to protect from corrosion. Painting is unlikely to be effective over long periods of time. If the pipe is made a cathode and the zinc plate is buried alongside, the plate is made an anode. By using a small potential difference applied between them, any corrosion which occurs will be on the anode, which can be cheaply renewed. So you're laying pipes, and you have a pipe out of iron, and you put another one out of zinc next to it. And that makes somehow the zinc to be the anode and the other one a cathode, or you make it intentionally. I don't know. One is now getting the electricity and the other one out or something. No. And there's no potential difference between them. So there's more electricity now going to either the iron or the zinc. And because the one is now the anode, because there's more going through it or something, more electricity, it is the zinc which is rusting, and not the iron. And the zinc is cheaper to replace. And you have to replace only the cheap zinc instead of the expensive iron pipe. Something like that. Let's do it again. If the pipe is made a cathode and the zinc plate is buried alongside, the plate is made an anode by using a small potential difference applied between them. Okay, you have two things, an iron pipe and a zinc pipe, and you yourself make you set a current out of them, you put them on under electricity, and you bring on one a little bit more, and therefore one of them is the cathode, the other one the anode. The current is just flowing from one to the other one. Because it flows from one to the other one, with this example with the spoon, it goes to the one. At the one place, the copper or the nickel are giving off into the solution, and the other one it comes onto the spoon. And by now saying from where to where the electricity is running, the current is running, you say where now the things are going to. And that way you can determine where the rust is happening, where the things are going to. Any corrosion which occurs will be at the anode, which can be cheaply renewed from time to time. You will remember that metals are deposited on a cathode and never removed from it. Hence the iron pipe cannot corrode as long as a small current flows towards it through the soil. This process is called cathodic protection. Having a battery, a wet soil iron pipe made a cathode, zinc plate made an anode. Okay, don't get it now completely, what I know, take me. But that is what we do. We're laying pipes, we're having an iron pipe and a zinc pipe, and so that the iron, the expensive iron, is not corroding, rusting. They're putting both under electricity. I don't know if they now actually do it now in the ground or whatever, but that is an option. That's somehow an idea at least. They're putting both under a current, and the one gets a little more than the other one, and therefore the electricity flows from the one to the other one or something, and therefore the iron is never rusting because the current runs every time I think from the iron to the zinc. And therefore there are never these rust particles or whatever, this whatever it was now, this hydrogen volcanic cell or some dilute sulfuric acids, whatever, the things are going to the other one, and the rusting is happening on the zinc pipeline and not on the iron. You can just replace the zinc and have an unrusted iron. We're going to understand that later better, but for now I think that is a fantastic idea. That was the electrical engineering part. If you were here for electrical engineering, you can go directly to the next part of electrical engineering. If you stay here and participate in the short, and we don't have enough time, extensor kappa and now strength training, then it's very obvious. We're having the fists next to us. We're bringing them down and again up. 3 rules. First rule, if you feel pain, stop immediately. Second rule, go only as far as you can go with a little bit of effort. Now fists and up and then down. And third rule, we just want to strengthen, not to exhaust, so don't overdo it. And now you will use a sock, a towel, a t-shirt, press onto it, and bring the arm to the outside. And again to the inside. Outside and inside. Now take the arm from the top and bring it down and up. One more time, down and upper arm. Take it, press evenly with all fingers onto it. Turn to the inside, only as far as it goes, all plainness. Out to the other side. Again inside. And now from the top, and bring the hand down. And now just press the neutral position. And the same with your hand. that was the shortened extensor copper and our strap fitting. Thank you very much, and have a next.